Hello, this is Sapath, and I'm an application engineer with the engineering simulation team in Bentley Systems. Welcome to this lecture on basics of structural analysis and design. This is a first video in the series of lectures on basics of structural analysis and design, and today we are discussing Introduction to Structural Engineering. In the upcoming lectures of this series, we will see how creation of a structural model and its analysis is done using STAAD.Pro. In today's lecture, we will discuss in brief about the different types of structures and the ways in which we can analyze them. We will also get familiar with some theoretical aspects which need to be understood before one can actually perform an analysis and design on a structure. The objective here is not to learn everything in excruciating detail, but have an overall awareness of what a student of structural engineering should understand. Finally, I will give you a short overview of STAAD.Pro, which is the structural analysis and design program that we are going to use in the next lectures. Let's start from the very basic question of what is a structure. It's basically a system which is made up of several individual structural elements that in combination will support certain types of loading. Some of the most common structural elements that you will see are beams, columns, and tie rods. Beams are usually straight and horizontal members that are mainly used to carry vertical loads, and they are primarily designed for resisting bending moment. Depending on the type of the structure, the material used for a beam can be reinforced concrete, metal like steel and aluminum, and also timber. If concrete is the material used, then rectangular sections are mostly applied. For a steel or an aluminum beam, you will generally see an I or H section being used. Columns are generally vertical members that resist axial compression loads. Occasionally, columns will experience both axial loads as well as bending moments. The most common sections used for a column are circular and square for reinforced concrete columns, and tubes and wide flange sections for steel and aluminum columns. Tie rods are members that only take tensile force, and as such, they are usually slender in comparison to other structural elements. Rods, bars, angles, and channels are the most used section types for tie rod. As mentioned before, a structure is a system made up of a combination of different structural elements. Depending on the different ways in which this combination can be configured, we get different types of structures, which is broadly classified into these four categories. So let's briefly discuss each one of them. Trusses are utilized when the required span is large and the depth of the structure is not an important criteria. They are comprised of slender members, usually configured in a triangular fashion. A truss is referred to as a plane truss when the members lie in a single plane, and this type can be seen often in bridges. Space trusses, on the other hand, have members extending in 3 dimensions and are suitable for derricks and towers. Cables and arches are also used to span long distances. Cables are usually flexible and carry their loads in tension. They are commonly used to support bridges and building roofs. Over to the right, we can see another application of cables in a cable-stayed tower. An arch receives its strength in compression, and arches are frequently used in bridges and dome roofs. Frames are frequently used in buildings, and the main structural elements in this system are beams and columns. Like trusses, frames can also be either plane frame system or a space frame system. This frame shown over here is a space frame used in a typical 3-story building, and these types of structures are generally indeterminate. We will discuss what this means in the later parts of this video. A surface structure is made from a material having very small thickness compared to its other dimensions. A surface can be made of a flexible material, in which case it acts as a membrane that is subjected to pure tension. Or it can also be made of a rigid material like reinforced concrete, in which case they are referred to as thin plates or shells, and they support loads primarily in tension and compression with very little bending. Now that we have some idea of what a structure is, let's understand what analysis of a structure means. Structural analysis simply means determining the effects of loading on a structure and its structural elements. Loads are the external forces acting on a structure, which are typically applied based on codes and local specifications. These loads will generate effects like the internal stresses in a structure, that would be axial force, shear force, and bending moments. Also, the structure will undergo some displacement due to the external loading. A structural analysis aims to calculate all of these effects. Based on codes and local specifications, a structure has to be analyzed for different loads. Dead loads are the type of loads that will permanently stay with the structure throughout its lifetime. These include loads from walls, floor fills, ceilings, other types of finishing works, and also the self-weight of the structure. Imposed loads or live loads are temporary loads that don't act always, but they have to be considered in the analysis. They should account for things like gathering of people, storage of materials, and so on. There are also lateral loads, whose main components are horizontal loads acting on a structure, like, for example, seismic loads. While seismic loads are only applied horizontally in a typical case, for a wind load, the uplift is also very important. As discussed previously, there are also several effects on the structures due to these types of external loading, and those effects are internal loads and displacements. And then there's also another effect, which is the reactions developed at the supports. The foundations for a structure are sized and designed according to the support reactions, so these are also very important to calculate. After the structural analysis is complete, the structural elements need to be proportioned so that they have adequate strength and stiffness to resist the internal forces without going excess deformation or without failure. Once we proportion the structural elements by changing the sections, dimensions, etc., the analysis will be outdated. So this is because the self-weight and the stiffness of the structure will change. Hence, the structure has to be reanalyzed, accounting for a more accurate determination of the weight of the members, their size and stiffness. This process of reanalyzing and proportioning is repeated until new changes in structural elements are no longer required based on the latest analysis. There are certain requirements according to design codes that need to be met to make the design acceptable. These requirements are known as design criteria. And the state of a structure beyond which it no longer satisfies the design criteria is known as limit state. Beyond the serviceability limit state, service criteria of codes like limits on deformations are no longer met. Ultimate limit state, however, are associated with major structural failure, like collapse of the structure. The design criteria must be met not only for individual loads acting on the structure separately, but also for combinations of loads because many load types can act simultaneously on a structure. But the maximum value of all the loads might not occur at the same time. Hence, a load combination does not mean adding the full influence of each load action together, but using a specified set of design values for simultaneous influence of different load actions. These set of design values to formulate load combinations for different limit states can be found in the design codes. In addition to this load uncertainty, load combinations also account for material uncertainty. Load combination of ultimate and serviceability limit states for Australia can be referred to from the Australian standard AS/NZS 1170. In addition to guidelines on loading and combinations, codes also provide acceptable rules for design and detail. Details on properties of materials, general and minimum design requirements, and procedures for design. Here is a list of some important Australian codes for structural engineers. Structural analysis for a system composed of linear elastic materials applies the principle of superposition. By utilizing this principle, results for combined effect of loads are calculated by superimposing the results of individual loads. This saves time in the analysis, as loads are not analyzed separately. This, however, is only applicable if Hooke's law is valid and if the geometry of the structure does not change significantly due to large displacements. As such, huge displacements will significantly change the position and orientation of the loads. Before we discuss the different methods of analysis, let's see what are some idealizations applied before the analysis is performed. Solution of many problems of physics begin with assumptions to simplify the problem and make it more practical. It is also the case in structural analysis, where many idealizations are essential because an exact analysis of the structure can never be carried out. So, estimates are made on the strength of materials, point of application of loads, support conditions, etc. The idealization of support connections are done mainly in three ways, assuming them to be the fixed, pinned, or roller support. A pin-connected joint and a roller support allows some freedom for rotation, whereas a fixed joint allows no relative rotation between the connected members, and as a result, it is consequently more expensive to fabricate. In reality, however, a pinned connection fabricated at site will also provide some degree of resistance to rotation, and there are also no perfectly fixed and roller supports. But these idealizations are made to make the problem more practical. After making idealizations with connections, members can be represented as lines so that we can establish an idealized model that can be used for analysis. And the tributary loadings on slabs can also be determined by also idealizing the slab as one-way or two-way slab. After we have an idealized model, we need to find out the determinacy of the structure so that we can choose the right method for analysis. Whether the idealized structural model is statically determinate or not can be determined based on the number of members and reactions. The forces in a determinate system can be found completely by solving the equilibrium equations, whereas for an indeterminate structure, we would be required to solve additional equations to get all the forces. For a truss, the determinacy depends on the number of members, reactions, and joints. If the truss is statically determinate, the method of joints can be used to determine the forces. If the forces in only a few members of a truss are to be found, the method of sections gives a direct means of obtaining these forces in a statically determinate truss. Along with the determination of forces, there are also different methods for calculating the deflections. Common methods are the double integration method, moment area method, and conjugate beam method. So far, we have discussed the analysis of a statically determinate truss structure where the equilibrium equations were sufficient. But majority of the structures today, which are designed in modern engineering, are statically indeterminate. This is mainly due to added members and supports, and also due to general form of the structure. Reinforced concrete buildings, for example, are nearly always indeterminate, because the beams and columns are casted as continuous members through the joints and over the supports. Although the structural analysis is complex in comparison to determinate structures, the indeterminate structures generally have smaller internal stresses and deflections for the same loading. Methods for analyzing statically indeterminate structures are listed here. The force method is not suitable for very highly indeterminate structures. In this method, the required additional equations are formed by writing equations to relate the unknown forces or moments in the structure. In comparison to the force method, slope deflection method requires less work to both formulate and solve the necessary equations, but it is not suitable for a system with very high degree of freedom. In slope deflection methods, additional equations required are formed by relating the unknown slopes and deflections to the applied loads on the structure. With the moment distribution method, equilibrium moment is determined at a locked joint, which is then distributed to the connecting members. A portion of this distributed moment is carried over to the other side of the span. This series of approximations or iterations is continued until the carryover moments become acceptably small, and in that case, the iterations will conclude. Moment distribution method can handle greater degree of indeterminacy and freedom in comparison to the previous two methods, but even then, the analysis of moderately complex structures can take many iterations using this method. So all of these three methods are practically only used to perform quick calculations for simple structures. Complex modern structures are typically analyzed using the matrix method. It is also easier to formulate in a computer, and even more so for the stiffness matrix method, which utilizes the same procedure for statically determinate as well as indeterminate structures. Whereas for the force method, there are different procedures for statically determinate and indeterminate structures. So let's look at this preferred method of stiffness matrix method in a little more detail. The stiffness matrix method is also a displacement method of analysis, like the slope displacement method and moment distribution method. In all displacement methods, including the stiffness matrix method, finding the degree of freedom is very essential. Locations of joints, supports, ends of a member, or locations where the members have a sudden change in cross-section are identified as nodes, and these nodes undergo displacements when the structure is loaded, and the possible number of independent motion available at these nodes is known as the degree of freedom. Unconstrained degrees of freedom are the degrees of freedom that are not constrained by a connection to a fixed structure, and therefore the node is allowed to move about freely in that direction. Constrained degrees of freedom are the degrees of freedom that are constrained by a connection to a fixed structure, and therefore the node is allowed to experience no movement in that direction. Example of constrained and unconstrained degree of freedom for a hinge and a roller support are shown in this figure. For a fixed support, all the degrees of freedom are constrained. In slope deflection method and moment distribution method, each degree of freedom is dealt with separately. For example, in a slope deflection method, one equation for each unconstrained degree of freedom is formulated, and unknown displacements and rotations are found out. In stiffness matrix method, we will end up with the same equations, but the equations are constructed using matrices that represent each element's stiffness. Grouping all the small matrices together, a stiffness matrix for the entire structure is created. Once it is established, the unknown displacements of the nodes can then be determined for any given loading on the structure. When these displacements are known, the external and internal forces in the structure can be calculated using force displacement relations for each member. Once the analysis is complete, the structural elements can be designed based on code requirements. The Australian code for concrete structures is the AS 3600, where you can find strength and serviceability design requirements for structural elements like concrete beams, columns, and slabs. The Australian code for steel structure is the AS 4100, where you can find design procedures for steel members subjected to axial tension, axial compression, bending, and combined action, and much more. Now let's discuss STAAD.Pro. STAAD.Pro Connect Edition is the most popular structural engineering software worldwide for 3D model generation, analysis, and multi-material design. It has an intuitive, user-friendly graphical user interface, visualization tools, powerful analysis and design facilities, and also integration to several other modeling and design software products. The program is organized to reflect the typical process of modeling, analyzing, and post-processing of a structure. The workflow panel in STAAD.Pro groups all the common tasks associated with a major stage of your structural project. Within each workflow of the workflow panel, there are a series of pages available which lay out the order of that workflow. Though it is not required, it is recommended to work from left to right along the pages within any workflow. The graphical window, view window, allows you to view the models or portions of the models using selected views. This is where the model drawings and results are displayed in graphical form. You can use tools to draw your mode and models, as well as graphically assign loads or specifications. You can select and apply standard sections to your members from the section profile tables. You can also use standard shapes like square, rectangle, circular sections, as well as create your own sections. In STAAD.Pro, you can apply different support types to any node, and you can apply a load type from a range of different load items like member and nodal loads. Linear elastic analysis along with other advanced analysis commands are also available. You can check the structure for code requirements as well as perform the design automatically. We learned before in this video that computer programs these days use the stiffness matrix method most of the time for the structural analysis, and STAAD.Pro is no different in that aspect. It also utilizes the stiffness matrix method for the analysis. With the completion of analysis, you can view all results in the post-processor of the program. With this, the first video in the series is completed. In the next video, we are going to look into modeling of a structure using STAAD.Pro. Thank you for joining.